Let's start looking at the solution to this most recent quiz. Okay, in part A, what we're doing here is we want to solve for this inequality, which means we want to first um, isolate the absolute value expression, which we first will do by dividing by -2, which will mandate a flip of the sign. Okay, and then giving us 8. Then we can remove the absolute value bars by comparing the term inside, mainly the 3x minus 4 to 8 and its opposite, -8, with the opposite comparison. And then we work it from the middle on out and arrive at this solution interval. Okay. Similarly, the approach number 2, again, you have to start by isolating the absolute value expression, which you'll first do by subtracting 5, which will compare 3 absolute value x plus 4 to 12, then divide by 3 and giving you 4, at which point it's uh, pretty much the same procedure as with the first problem. Okay, the subsequent problems here. First one, we have to build a sign table to determine when this polynomial expression is less than 0. So we factor first by pulling out an x, and then factoring the remaining trinomial as shown here. Okay, the factors will contribute points um, on the sign table as indicated, mainly a 0, a -1/2, and a -8. So we line them up in increasing order, and the factors in the same sequence from top to bottom. Okay, and construct our sign table. X plus 8 will change signs left and right of 8. 2x plus 1 change signs left and right of -1/2. X change signs left and right of 0. So we are able to construct our sign table, take the product of signs. We're looking for the negative intervals, which prove to be -infinity to -8. Bracket that. And as well as -1/2 to 0. Okay. Moving down to the next problem. Okay. We simply want to pull everything to one side. So the x squared x plus 2 term is pulled over as a subtraction. This should have been recognized as a factorable by removing the common factor of x plus 2, giving us 9 minus x squared. I commonly would prefer to see this as x squared minus 9, so I can rewrite that at the expense of pulling out a -1. If I then divide both sides by that -1, I'll make it disappear at the expense of flipping the sign from a greater than to a less than. I factor. Okay, I build my sign table around my factors and those values causing zeros of my factors, and line it up as shown here. My interval here is wanting to establish a less than condition, so I want the negative intervals as tagged -infinity to -3, not inclusive, and then between -2 and 3. The next problem, factor everything numerator and denominator as shown. Once the denominator is factored, declare what x cannot equal. As you can see, 0, 4, and -1. Build the sign table around all these factors, including the 6x squared, which will always be positive because of the squaring. Okay. The sign table is then constructed as shown. The intervals where this is greater than 0. Okay. -infinity, -3. Some made the mistake of saying -1 up to 3, but recall it can't equal 0. So that cannot be written as a single interval, -1 to 3. It has to be written such that we do not include 0. If you put -1 through 3, then you're including 0. So the correct notation for that 2 intervals is as stated below. Okay, and we also pick up the interval from 4 to 0. Okay, the last problem, which caused a lot of grief for people, again, just if we could go back to this one, the sign table is built around factors and products and quotients of factors. That's how the signs work, because we're taking advantage of knowing that if you have an odd number of negatives that go positive, an even number of negatives an odd number of negatives go negative, an even number of negatives go positive. That's how things operate with factors with their signs, okay, under multiplication and division. So everything has got to be expressed in terms of factors, in terms of multiplication and division. So I think in previous videos illustrated that you cannot simply cross multiply. If that were an equation with an equal sign, that would be the thing to do. But because this is an inequality, and in an inequality we're forced to reverse the sign when we multiply by a negative, and we don't know under which conditions this is positive and negative. That's not the way to go. So we have to swing everything to one side. We got to put everything on a common denominator. Okay. If we modify the denominator, then we've got to appropriately modify the numerator as well, as shown here. Okay. Then you got to you cannot build a sign table at this point. I found people building a sign table here. Cannot build a sign table on this. We have to multiply these out. Excuse me. Multiply those out. Multiply this product of binomials, which of course is preceded by negative, so you want to pay special attention to that. And then expand it, combine your terms, and we come down to this. -2x plus 2 over x plus 2, x plus 1, where x can't equal -2 or -1. I chose to pull out the -2, okay, but it needs to be included in the sign table, which a lot of people got down to this point, which is good, but without including that -2 in the sign table, as you can see, staying negative all the way across, all your signs will have been opposite that which they were supposed to have been. So there's your sign table built around the factors, including the -2. Had that been a positive 2, it wouldn't have had any impact on the sign table. But the negative obviously is going to have an impact on the sign table. So okay, here's our interval satisfying this inequality. Okay, now on to the calculator part. This was meant to be quite simple. Okay, you're asked with this graph of the function as shown. Okay, we're all along there. Okay. When is this inequality less than 0? Okay, which is to mean when is the graph underneath the x-axis? Now, okay, it says underneath the x-axis without touching the x-axis. Now, some people were questioning themselves. That's as to where this crosses the x-axis. Well, you don't need to question yourself, okay? It crosses at 0 from this factor. It crosses at -1 from the x plus 1 to the 4th factor. And then it crosses at +1 from the other factor, from the x minus 1 factor. Okay, and there's the graph. So now it'd be a much different statement if this had read when is this less than or equal to, because then we could just say, oh, from -infinity all the way up to 1, But because we can't include 0, we have to partition it into the 3 groupings: negative infinity, -1, -1 to 0, and then 1, and then 0 to -1. These two were calculator-based problems, so let's take a look at the calculator. Pull that up. Okay. That then is the graph of this first expression, x cubed minus 5x squared plus 8x minus 1. Okay, so go back to the graph. We want to know when is that greater than or equal to 0, which is saying when is it above the x-axis, which means we have to find that x-intercept, so we know we could obviously see from that point in x on up, it's greater than 0. So F5, option 2, zeros. A little bit left to the intersection, or the intercept, enter. Scroll a little bit to the right, enter. Let it do its work. The point, okay, of the x-intercept, as we can see, it's a 3 decimal place accuracy, 0.136. And from that value of x on out, the graph, the function, will always be above the axis. Looking at the next one, okay, go back. I have that set up. I'm just going to turn that guy off and turn on Y2. We're wanting to know, okay, when is, well, what I did actually here was to say, well, look, I'm going to pull the 2 over, and if I pull the 2 over, then I'm comparing it to 0. So I'm graphing 3 over 2 minus x minus 2, and basically want to know when that's greater than 0. So taking a look at the graph, okay, we can see that it's greater than 0 from this intercept on up to this asymptote, which occurs at 2, not -2, mind you, have to make that correction there. Okay, and so we have to find that point, and that's an F5. Find the 0, and left bound, enter. Scroll a little bit above the intercept, right bound. Okay, and that's a half, as you can see, all the way out to 2, and as I said, not that -2, so we will correct that. Okay, and that is the entire test reviewed for you.